Okay, so let us start the week 5 tutorial of the course Introductory Organic Chemistry 1 conducted by NPTEL, whose course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputre from ISER Pune. I'm your PMRF teaching assistant Deepika and I'm doing PhD in chemistry at IIT Bombay. The video lecture recording of this tutorial can also be found in YouTube. So I welcome you all for the question solving approaches of today's tutorial. So let us quickly revise the types of reactions that alkene undergo. In this week video lectures, Neeraja ma'am had taken classes on various reactions of alkenes. She showed how and what kind of mechanisms alkenes follow when it comes to reacting with various reagents. Alkenes undergo various reactions like hydrohalonation, acid catalyzed hydration, oxymercuration, demercuration, hydroboration, oxidation, halogenation, halohydrine, hydrogenation, and so on. So, in today's tutorial, we are going to solve a few questions on these topics, and we will try to solve the questions by thoroughly looking at the mechanisms that these reactions are going to follow. So in the first question, you have to react this epoxide, which is pentene oxide molecule, and you have to react with HCl in presence of methanol solvent. So you are just given the epoxide moiety and in presence of hydrochloric acid in methanol. So what kind of reaction that epoxide can undergo? In last week's session, we learned about acidity and basicity, and following those concepts, you can easily think of treating this epoxide with acid in a way that the lone pair of oxygen gets involved in the mechanism at the first stage. So, when you treat an epoxide with acid, what happens now? The lone pair of oxygen present will abstract a proton, which is acidic proton, from the medium to form this oxonium ion. This oxonium cation will now be attacked by water molecule present in the system, because this oxonium ion formed is highly unstable, so it will be facile to break the oxonium ring using water molecule present in the system. So what happens? This water molecule will attack at either side of this epoxide ring, and eventually this epoxide, the oxonium earlier formed, will be broken down. So this gets neutralized because arrow is coming to the positive charge, whereas this oxygen atom of water molecule is giving its lone pair of electron to open up the ring. So firstly you will get a positive charge on this oxygen of water molecule and also neutralize this oxygen. So in this position, first you will get a hydroxyl group due to opening of epoxide ring. But at this position you will have OH2, where oxygen will have a positive charge initially. Then what you have to do? You have to remove a proton from the oxonium now formed. Okay. In the second step, you get another oxonium by the attack of lone pair of oxygen molecule in water to open up the ring, when you get a positive charge on the on the oxygen atom of water molecule. So one proton, if you knock out from the oxonium, you will finally get a trans 1,2 diol here. Okay, you have to always remember that after formation of the first oxonium ion, when the lone pair of oxygen gives its electron to acidic proton, the water molecule will attack the epoxide ring from the opposite face. Okay, it is always preferred from the opposite face. It is because, see, here you have donation of electrons from N to sigma star. Okay, N orbital of oxygen atom and sigma star of this oxonium oxygen. So actually what happens now, the molecular orbitals are arranged in such a way that if you want to donate electrons from one species to the other, due to the molecular orbital orientation, you have to consider the attack of the water molecule from the opposite face always. Okay, if it comes from this way, it cannot efficiently donate the n orbital electrons of the oxygen atom to the sigma star of this bond. Okay, so because of this fact, you have to always consider the attack from the below face. And then finally you get a trans 1,2 diol in this reaction of an epoxide with acid. So in our question, we had to treat this pentene oxide with hydrochloric acid in presence of methanol. So just like the mechanism I have shown you now, you can easily guess the product. What will it be? The product will be a trans 1,2 diol. I hope this is clear how the mechanism went ahead. This oxygen atom will first be protonated to give an oxonium ion, and then the water molecule will attack, leading to the opening of the oxonium, and then one proton from the water oxonium now you will be removed to give you a trans 1,2 diol as a product. Of course, you can show the enantiomer of this also, like this CO bond, if you show below, if you show above, and this CO bond, if you show below, that will be also the correct answer for this question, because the product will be racemic. So either of the enantiomer you can show, but just remember you have to show both the alcoholic groups in a trans fashion. Remember that thing. You cannot show in a syn hydroxylation, syn dihydroxyl substituents you cannot show for epoxide opening in presence of acid. Okay, because the mechanism I have already explained. I hope this is clear. So first question we have already approached. In the next question, you have to treat this alkene with hydrochloric acid. So in this question, what you have to do, what happens when you treat an alkene in hydrochloric acid, this pi bond present in the alkene is electron rich and nucleophilic. Okay, and HCl is capable of donating protons. So what happens is this nucleophilic pi bond will attack and take up a proton from the acidic medium, and in turn it will form this carbocation. Okay, because the double bond is giving its electron pair, it will get converted into a positive charge, whereas from acidic medium it is taking a proton H plus, so the H plus will get neutralized in turn. You might think that why we are not attaching the incoming proton to this position and we are not getting a carbocation at this position. You might think that, but that can be rationalized by the stability of carbocation series. Okay, you can go ahead by the stability of carbocations as primary carbon is less stable than secondary carbocation, and which is less stable than tertiary carbocation. If you had gotten a carbocation here, that would have been a secondary one. Whereas in the product, what you are getting is tertiary one. So definitely tertiary carbocation will be more stable than the secondary one. So you get this one preferably. Okay. So then in the next step, the tertiary carbocation which is formed will be attacked by a chloride anion present in the system. Okay. The charged species will be trapped by the chloride anion in the system, and you will get a product in which the chloride anion will be present in the position where you got a tertiary carbocation. So if you are asked that is this reaction following Markovnikov rule or not? Markovnikov regioselectivity is being followed here or not? If you see that H and Cl are getting added across this double bond, then you in the final product what you are seeing is hydrogen is getting added here and chloride is getting added here. So yes, this is definitely following the Markovnikov regioselectivity because the hydrogen is getting added to the position which contains more number of hydrogen already. Here you already had one hydrogen and the new proton is getting added here only. So yes, in the example, Markovnikov regioselectivity is being followed. And you finally get this product which is chloromethyl cyclohexane. Then moving to the third question, which is a similar question, but just the substrate is acyclic. Okay. So here you have to treat pentene with an acidic system. What will happen if this acyclic molecule pentene will be treated with hydrochloric acid medium? Like we solved the earlier question, what happens? The double bond, the pi bond in the molecule is nucleophilic due to being electron rich. So this electron rich double bond will extract a proton from the system. Okay, and in turn the chloride anion will be knocked out. So in turn what you get is two kinds of carbocation like I showed in the earlier case. So between these two carbocations, now you have to compare the stability of these two. Like I said, secondary carbocation is more stable than the primary one. So this secondary carbocation will be predominantly formed in this reaction. So in first step you get a secondary carbocation. Now what happens? The counter anion chloride is there present in the system. So it will try to neutralize this charged species present. So the chloride anion will now attack at the secondary carbocation. And this will lead to the formation of 2-chlorobutane. So in our example, we had pentene. Na? So the finally as product you will get the chlorine atom here following the Markovnikov rule as well. The chlorine atom will be present here and hydrogen will get added here. So you get 2-chloropentane. See, if you had obtained the primary carbocation, you would have obtained chlorination at the carbon number 1, leading to the formation of 1-chloropentane in our case. But the less stable carbocation will not form, so getting the chance of obtaining this product is nullified, and you get 2-chloropentane as the product here. Okay, so you just have to remember the mechanism, how the arrows are approaching depending on the nucleophilicity and electrophilicity of the partners in the reaction, and you can easily figure out what kind of carbocations are forming, what kind of intermediates are forming, and finally what product you obtain. So moving to the fourth question of today's tutorial. Here another acyclic alkene molecule is given. You have to treat it with hydrochloric acid, but this time this one is not linear. Okay, so you have to treat this molecule with hydrochloric acid medium. Like the other two examples solved earlier, you can approach in the similar way. Okay, the double bond will first attack at the hydrogen, the proton of HCl. Then you get a secondary carbocation. So what happens? Although you get a secondary carbocation, by nullifying the chance of getting carbocation in this position, you have to observe the fact that the adjacent carbon atom of this carbocation is tertiary, having 3 methyl groups present. So when such kind of situations arise, that the adjacent carbon atom is tertiary, and if you can shift a methyl group to the secondary carbocation already formed, you get a tertiary carbocation this time. Okay, if you have such a situation in the system, then the carbocation primarily formed will undergo a rearrangement, leading to the formation of even more stable carbocation. So see what happens. Earlier you are getting a secondary carbocation, but if you can shift a methyl from this position to the secondary carbocation, this positive charge will get neutralized. But now, since one methyl group has left, this carbon has donated its methyl group, this carbon will become positive, which is a tertiary carbocation. So you can ask, what is the driving force of this methyl shift? Because just like that, you cannot break a carbon-carbon bond. It is very strong. So the driving force is definitely getting a more stable carbocation. Because lastly, you are getting a tertiary carbocation. So always remember, if you have a chance of getting a more stable carbocation in the reaction sequence, then always go for that pathway and form the most stable carbocation as the reactive intermediate. So after you are done identifying that what will be the actual carbocation being formed in the system, you can now attack attack the positively charged carbon atom by this chloride anion, which was present in the system. So although you get this secondary carbocation primarily, the chloride anion will not attack at this carbon first, because right after formation of the secondary carbocation, as soon as possible, one methyl will shift from this carbon to here to give you this more stable carbocation. And thus, for this substrate, you obtain a product which is 2-chloro-2,3-dimethyl butane. So, this is also following the carbocation mechanism, but definitely the first carbocation you obtained got rearranged to a more stable carbocation. So I hope this is clear. Now moving ahead to the question number 5. Now you have another cyclic system which is indene. Okay. So you have to treat this indene system with hydrobromic acid. What will happen if you treat this double bond which is present endo to this indene molecule? You can approach the question in a similar way that we just now discussed. Okay, in presence of acid, you always get a carbocation in the first step. So let us try to solve this question. This double bond, being nucleophilic and electron rich, will first extract a proton from hydrobromic acid. So taking up the acidic proton, the bromide will get knocked out and you get a positive charge at this position. Okay, you get this tertiary carbocation eventually. You can also think like the earlier cases that why are we not adding the hydrogen here and forming the carbocation here. You have to again look at the stability of the carbocation formed. If you had obtained a positive charge here, it would have been a secondary one. But if you are adding the hydrogen here and forming the positive charge here, you are getting the more stable carbocation, which is a tertiary one. So you get this tertiary carbocation in the reaction, and then in the simultaneous step, the bromide ion which was gotten knocked out will attack at the carbocation, and in turn you will get this bromo substituted indene. Bromide will come at this tertiary carbocation forming position. So the product is bromo-indene. Okay. Now let us solve the question number 6, which should be easy enough already because we have discussed a lot of questions already on this concept. But do not forget to look at the fact whether you can form more stable carbocation than the already formed one or not. Okay, because at last you have to form the most stable carbocation which is possible. Keeping this in mind, let us move to question number 6, where you have to treat this alkene with hydrochloric acid. What happens? The alkene, the double bond, carbon-carbon double bond, the pi bond will attack at hydrochloric acid and extract the proton, leading to the formation of a secondary carbocation at this position. So you must have already known you cannot add the hydrogen here and get primary carbocation here. So first you will get the secondary carbocation. We have obtained the first carbocation. Now you have to see that Thus, the adjacent carbon of this carbocation possess transferable substituents which can lead to the formation of a more stable carbocation. You can see, does it have? It has this alkyl substituent, it has this alkyl substituent and one hydrogen here. So what happens in this reaction sequence? You eventually get a hydrogen shift from this carbon to this carbocation, leading to the formation of a more stable carbocation, which is tertiary one. Okay, at this ring junction you get a carbocation by shifting a proton to this carbocation formed. If you had no proton at this position, you should have think of shifting the alkyl substituents present. Okay, like in earlier case now we found the adjacent carbon atom was connected to 3 methyl groups where you had to shift one methyl to get the tertiary carbocation which was more stable. So here also you have to shift a proton from this position to this, and you, since you are shifting and donating your electron pairs in the form of hydrogen, this position will get neutralized. But since this carbon is donating its electron pairs in presence of hydride, then this will get a positive charge this time. So you end up getting a tertiary carbocation which will be attacked by the chloride anion present, and you get this chlorine substituent at the junction of the ring. Thus, the final product formed in the reaction you get is chloroethyl cyclohexane. I hope you understood that first you form the more stable carbocation by protonating this double bond, and then you shifted one proton from this position to this to get the more stable carbocation, which was a tertiary one. So in such cases you always have to look at the adjacent position carbon. If you are getting a more stable carbocation, then just go for it. So till now we saw that how alkenes and epoxides were reacting with hydrochloric and hydrobromic acid systems. Now you are given this acyclic pentene system and you have to react it with acidic system. They are not mentioning whether it is hydrochloric or hydrobromic, etc., etc., but you have to solve the question in the similar way. Okay, just like you observed. But yes, here you don't have a counter anion like in earlier cases you got bromide or chloride which attacked the carbocation formed, but here you have water molecules in the system. Okay, so in these cases water molecules will give the nucleophilic substitution. So if we look at the mechanism step by step, the electron rich double bond will attack on the proton, acidic proton which is present in the acidic medium, leading to the formation of the more stable carbocation out of the possible ways. You can either get a primary or secondary here, but you have to prefer the more stable one. So we are getting a secondary carbocation in the first step. Then water molecule this time will act as nucleophilic agent, and the oxygen lone pair will donate electron pairs to the carbocation. So what happens? You're donating electron pair to a positive center. So the positive charge on carbocation will get neutralized, because whenever you are donating electron pairs to a positive center, it will get neutralized, and In turn, whatever is giving up its electrons will get positively charged. Okay, that is a old concept. So this, since this oxygen is giving its lone pair of electrons to the positively charged carbocation, this oxygen in turn will get positively charged. Now what you have to do, you have more number of water molecules in the system. Those will extract a proton from this oxonium ion, and it will try to neutralize this charged species which is formed. So in the final step, what you get is this proton will be removed and the positive charge will get neutralized. You can imagine, like for example, suppose this is another water molecule. Oxygen will take out this proton of the oxonium, and then this bond will form and the electron pairs will be pushed to the positively charged oxygen, and in turn it will get neutralized. So you end up getting a neutral moiety this time, and the product is 2-hydroxypentene. So like you get at the 2 position of this the parent pentane parent pentane framework, you get the hydroxy substituent at the second position. So that was the mechanism when you have only acidic medium and no chloride or bromide counter anion to attack at the carbocation. I hope that was clear. But also you have to remember that in these cases as well, you have to look for the formation of more stable carbocation. And if you have chances of getting more stable carbocation by rearrangement or uh, hydrogen or methyl shift, etc., so then you have to go for that and finally get the more stable carbocation. So moving to the question number 9, similar example we have discussed in presence of HCl. Now you have only an acidic medium. So you have to answer what happens in presence of uh, acidic medium to this molecule. So you have 3-methyl-1-pentene where this pi bond is electron rich, and as usual it will attack on an acidic proton present in the system. So if you attack on a proton via this double bond, you will get a positive charge on this carbon. Okay, leading to the formation of a secondary carbocation, because this one will be more stable than the primary one which you had gotten here. So you end up getting a secondary one. Now you have to look at its adjacent carbon. The adjacent carbon is containing one methyl group, one ethyl group, and the hydrogen atom. Okay, like a proton here. So what happens to get a tertiary carbocation at this position in the final pre-final step? You just shift a proton from this carbon which is attached to this carbon to this secondary carbocation formed. Okay, so after shifting the proton to this carbon, we're donating the hydride to the secondary carbocation. So you have to neutralize the charge on the secondary carbocation. Okay, and by shifting the proton to this secondary carbocation, you get positive charge here, which is a tertiary one. So you end up getting this tertiary carbocation. Then the tertiary carbocation will be attacked by water molecules present in the system, just like the earlier question we saw. Okay, first water molecule will attack on this carbocation, leading to the formation of an oxonium ion, and this carbocation position will get neutralized, and then from the oxonium formed here, one proton will be removed, leading to the formation of neutral OH functionality at this position. So you end up getting this product in the reaction. So you should never forget about the formation of more stable carbocation in the course of the mechanism. Okay, otherwise you will end up making mistakes. What if you had ignored the hydride shift from this position and just attacked the water molecule here? You would have gotten a completely different product, which could also be formed, but this product will be the major product because the major reactive intermediate that you are getting in the mechanism is the tertiary one. Okay, so do not make such mistakes and always form the more stable carbocation finally. After this, we are moving to question number 10. So in this question, you have to react this cyclic alkene with mercuric acetate in water, which in which you will get a product, and you have to subject the product with sodium borohydride. So what happens if you react this internal alkene, which is methyl substituted, with mercury acetate? This mechanism is somewhat similar to that what we have observed in case of HCl, HBr, and acidic systems. We had always attacked the electrophilic species from the electron reach double bond of the alkene. So here also you have to do the same thing. Okay, what happens? First, the double bond. Let us take the example of this alkene. First, the double bond will attack at the mercury acetate, and after attacking it will form this mercurinium ion. Okay, because this double bond is, although this double bond is leaving its electron pair to mercury, this acetate ion is now being knocked out. Like for example, in last week's tutorial, we saw how iodination was happening with alkene. So similarly, you used to get iodination via an intermediate, in which you used to get this three-membered reactive intermediate. Similarly, in this case as well, you get this mercurinium ion. So now this mercurinium ion will first open up. Okay, because this three-membered ring is highly strained, so it will try to relax and it will get opened up. In turn, this bond will break. I will tell why particularly this bond will break, not this one. But before that, let us see what happens actually. This bond will break, the electron pair will be pushed to mercury, and you get a positive charge in this position. Forget about water, okay? Water molecule has not come to the system yet. You have to first open up the mercurinium anion, which is highly strained and unstable. So you open the ring through this side, you get mercury center neutralized, and you get a positive charge here, which is a secondary carbocation. What would have happened if we opened the three-membered ring from this side? If you had opened this from this side, yes, the mercury center would have gotten neutralized, but in turn you would have gotten a primary carbocation here, okay, which is not stable as secondary carbocation. So we will always prefer the secondary carbocation here. So you have to break the bond from this side. So till now you have gotten a secondary carbocation at this position. After this, water is present in the system. Mercury acetate in water. So water is present in the system. Water will now neutralize the secondary carbocation formed, just like the earlier two examples we saw. So the water molecule will donate its electron pair to this secondary carbocation formed. In turn, you get a oxonium and oxonium cation here. And definitely due to electron pair donation, this center will now get neutralized, which was a secondary carbocation earlier. So carbocation is neutralized and you get this oxonium, and now you have to eliminate one proton which would be taken out by water. Okay, so one proton will get knocked out to give this neutral molecule. Okay, so the first step product will be this mercury acetate species, where you can see that across this double bond, OH is forming at this position and mercury acetate fragment is getting attached at this position. Now, upon treatment of the species formed here with sodium borohydride, you get hydride donation from NaBH4 to this position, and this weak carbon mercury bond will get broken down. So eventually you end up getting a hydride addition at this position, which will substitute this mercury acetate moiety. So overall, you can see over the two steps, you are adding a water molecule across this double bond. Okay, combining the two steps, combining both the steps in the reaction, you are overall adding a water molecule across this. Water molecule, that means H plus and OH minus, you are adding across this double bond. So look at the product that you are getting. Hydroxyl group is coming at this position where the methyl substituent was present, and hydrogen of the imaginary water molecule is getting added here. So the reaction mechanism is following the Markovnikov radioselectivity, because the hydrogen, that means the hydride at last, is eventually getting added following the Markovnikov rule. Thus, if you treat this methyl substituted cyclopentene with mercury acetate in water followed by treatment with sodium borohydride, you get this tertiary alcohol. Okay, I hope this was clear to you. So next example is also very similar. The approach will be same. The nucleophilic double bond will attack at the electrophilic center, and then water will come to the picture, and lastly you will have to treat the mercury acetate species formed with sodium borohydride. So similar mechanism it will also follow. You will get uh, mercury acetate at this position, and you will finally get a hydride donation from the sodium borohydride molecule to this position, which will replace the mercury acetate. Okay, so you end up getting this alcohol as the product. Moving to the next question. Now you have hydrogenation of alkene. So hydrogenation happens when you first adsorb hydrogen on a metal surface or a support, and then you bring the alkene to the system, and the hydrogens in the adsorbed on the surface gets added to the alkene in a syn fashion. So let us see how it is happening. First, like I said, the hydrogen molecule will get attached, adsorbed on the catalyst surface. Here the catalyst is platinum, and then you bring the alkene on the system. The alkene will also get adsorbed on the system, okay? Adsorbed on the catalyst surface. So now what happens? The hydrogens adsorbed will get added one by one to the alkene adsorbed. Like first, one hydrogen and catalyst coordinating bond will break and it gets added to the alkene in this side. Simultaneously, the other hydrogen adsorbed will also get added to the other side carbon atom. And you get syn addition of hydrogen, two hydrogen atoms to the alkene, giving a saturated hydrocarbon. So this hydrogenation in presence of metal catalyst follow a mechanism of adsorption. Okay, it is more like physical chemistry process. So after adsorption, you observe hydrogen transfer to the alkene, which was also adsorbed on the system. So thus, in this question, you get this saturated hydrocarbon. You hydrogenate the alkene present. Coming to the next question, where you have to now brominate one alkene. You have to treat this methyl substituted cyclopentene with bromine in DCM solvent. Okay, DCM is solvent. So what will happen if you treat this double bond of this alkene with bromine? Similar kind of mechanism we have already discussed in one of our earlier tutorial. So let us go through the mechanism again. What happens? Let us take the example of cyclopentene first, okay? You get attack of this nucleophilic double bond at one bromine of the bromine molecule present in the system, and you end up getting and you end up knocking out the bromide anion of bromine, okay? So in turn, when this double bond is attacking at the at one bromine atom, you get a reactive intermediate which is named as bromonium ion, in which both the carbon atoms will form coordination with the bromine. Okay, initially both the carbon atoms will get involved with the bromine atom, leading to the formation of this cyclic bromonium ion. You must remember the cyclic bromonium ion is highly unstable and it immediately gets broken down by the counteranion bromide, which was gotten knocked out in the first step. So bromide will now come into the picture again, and this will attack either at this position or at this position, but in an anti fashion. Okay, bromide will attack on the bromonium from the opposite face here. What is the reason? The reason I had explained you already. It is due to the molecular orbital orientation. Okay, since here you are observing N2 sigma star electron donation, the orbitals involved in the donation are oriented in such a way that the incoming bromide anion can attack from the below face, from the opposite face only. So if you are forming this bromonium in the below phase, alpha phase, you have to attack the bromonium by this bromide anion from the beta phase, which is above the plane of the paper. So this bromide will come from this way, and in turn this ring will open up and electron pairs will be pushed to this positively charged bromine, and you get this dibromo cyclopentane. Okay, you get this dibromocyclopentane, not pentene. This is dibromocyclopentane. You may ask, what if you write this bromide above the plane and this bromide below the plane? That will also be the correct answer for this question. Okay, you eventually get this product and it's enantiomer. But like I said earlier, you have to keep both the bromine atoms in opposite phases. You cannot keep both the bromine in either alpha phase or both the bromine in beta phase. If you are keeping one bromine in alpha phase, the other will be have to kept in the opposite phase. So in this case, which was methyl substituted cyclopentane, you will get bromination in both these positions, in which one bromine will be above the plane and one bromine will be below the plane. Both the structures will be correct. Okay, you can just have to remember that bromine atoms have to be placed in a opposite phase. So moving to question number 17. Again, you have to now treat this alkene, which is acyclic. This acyclic internal alkene you have to treat with chlorine in DCM solvent. What will happen? Similar kind of mechanism will be followed. Okay, this acyclic alkene will first, let us take the example of bromine only, but the mechanism will be same. Okay, so the double bond will first attack on bromine of the bromine molecule. The other bromide will get knocked out by breaking the bond of bromine, and you get this bromonium intermediate like we saw in the earlier case. And the bromonium ion, being highly unstable, will be immediately broken down by the bromide anion. So this bromide anion can come from two ways this time, okay? Because the alkene you have in the example is unsymmetrical. Like in one position it is methyl substituted, in the other position, other side, it is ethyl substituted. So here selectivity question will come, that from which way the bromide will attack. From the from the methyl substituted carbon or from the ethyl substituted carbon. You can answer this question in two ways, okay? Number one, the incoming bromide will always prefer the less sterically hindered side. See, if you compare the steric bulkiness of methyl and ethyl, obviously methyl is less bulky. So the incoming bromide will prefer to attack from that side. And eventually you get the ring opened from this way, this side, okay? Also, you can consider the electron density factor as well, okay? See, the electron donating power of ethyl is higher than methyl, okay? So if you compare the electron density at these two positions, the incoming bromide is also carrying a negative charge, which is electron rich. So it will somehow get repelled by this more electron rich side. But always remember, the steric factor is the main cause for this attack, why bromide is coming from this way. But you can also think of the electron density present in these two positions. Since this position is more electron rich, it will repel the incoming bromide more. So the bromide has to go to this position, which is methyl substituted. So after the attack of bromide ion at this carbon atom, the three-membered bromonium ion will get broken down and you will get this anti-dibromo compound. Always remember, the bromide is coming from the opposite face. So both the bromine atoms will be placed in the opposite faces. So you can also look at the stereo centers present in the compound by converting it to the Fisher projection, and you see that the product you will obtain will be RNS. Okay, you can also write the enantiomer of this product like S here and R here, and that one will also be the correct answer. Okay, because in this example we have shown the formation of bromonium in the upper face, right? Like above the plane we are forming. But you can also observe formation of bromonium in the below face. Okay, so if you write S here and R configuration here, that answer will also be correct because you get the racemic product in this example. So you get this saturated compound when you treat the alkene with chlorine in DCM. So you get this dichloro compound in the similar fashion, but just in case of chlorine, you will get a chloronium ion in a similar fashion. In the next question, you have to treat this alkene with peracid. Okay, peracetic acid is in the system, which will be followed by addition of acidic water, and you have to treat the system in this way. So let us try to understand what is actually happening here. Okay, see, this oxygen atom, which is carrying the acidic proton of per acid, is highly electron deficient. Okay, because the electron pairs of this oxygen present are being pushed to the opposite direction of it due to being conjugated with this carbonyl group. So, because of being highly electron deficient, this oxygen will get reacted with the electron rich double bond present in the system, which is 1-methyl cyclohexene. And this double bond will attack at this highly electron deficient oxygen. If you push the arrows in this way to the electron pulling oxygen of the carbonyl, and in turn you shift this acidic proton of per acid and add to the double bond, you will get this epoxide ring formed and acetic acid as the byproduct. Okay, how is it happening? You have to see, I told you this oxygen atom is highly electron deficient here. So the double bond will attack here. You can also simply break this oxygen-oxygen bond because it is a peroxide bond and peroxide linkages are highly unstable and easily broken. So you have to break this peroxide linkage. O- will get knocked down and in acidic medium it will be protonated as acetic acid. So you have attack at this oxygen and this acidic proton will get transferred here. And overall you are getting 1-methyl cyclohexene oxide. This epoxide you are getting. So in the second step of the question, you are treating the epoxide with acidic water. What happens in acidic water? Water adds to the epoxide ring, which is highly strained. It gets aided and opens up the epoxide ring. So water molecule will come from the opposite face and undergo an N2 sigma star donation to this epoxide and open up this epoxide ring. First you have to imagine a proton coordination at this oxygen, okay, because this is the acidic water medium. In the second step we are treating, so this oxygen will get protonated just like we did example in the earlier cases. So this oxygen atom will get protonated to give you oxonium ion, and then the oxonium ion will get opened by water molecule from the opposite face, and this time the water molecule will attack from this side. From this side, from the opposite face, from above the plate. Why this side? Because I told you in the last example that the incoming nucleophile will prefer the less sterically hindered side and also less electron density side. So this will be the preferred one for the incoming water molecule. So water molecule will attack here and open up the epoxide ring to give you finally this diol system. Obviously this will be a racemic one. You can also write the below phase substituents above the plane and changing the stereochemistry of this hydroxyl to below the plane. Like the enantiomer also you can write, which will also be correct. So in this way, you get the final product that when you treat this epoxide formed in the first step of the reaction, when you treat it with acidic water, you first get an oxonium ion here by protonation, and then water will come from this side and open up the ring. So I hope this is clear, the reaction of peracetic acid with alkenes. You can also get you will also come across such examples where in place of peracetic acids you can also use a few other peracids like mostly MCPBA, metachloroperbenzoic acid, is most commonly used for such type of reactions. Okay, for such type of epoxidations of electron rich double bonds, you will come across this reagent which is called metachloroperbenzoic acid. That one is most commonly used. Then moving to the next question, here you have to treat this methyl substituted cyclohexene with osmium tetroxide in presence of hydrogen peroxide. Okay, so what will happen if you treat this alkene with osmium tetroxide, which is a very costly reagent. Okay, osmium tetroxide is highly costly, and let us understand the mechanism. Okay, actually this H2O, hydrogen peroxide, is not required. You just consider water molecule in the system. Okay, you just consider osmium tetroxide and water molecule present in the system. So first you add the osmium tetroxide species to the alkene, and you will get this transition state where two oxygen atoms of the osmium tetroxide are coordinating with the alkene double bond. And finally, it will lead to the formation of CO bonds with the osmium oxygen atoms and the alkene carbon atoms. And this species is called osmate ester. So you get osmate ester for the first step of the reaction when you add osmium tetroxide to the alkene. And in the final step, what happens? Water molecule will come. This will give its electron pair to this osmium, which will lead to the formation of this CO double bond. Okay, you have to just push the electrons using arrows. One electron pair will be donated from water to osmium, and in turn the arrow will flow to this oxygen atom. Okay, this oxygen osmium bond, which is weaker, is broken, and you get O minus here, which will be protonated to give hydroxy substituent. Okay, so now you have one hydroxy in the osmium and one hydroxy here. Okay, by after protonation of O minus. So in this side CO bond also you will get the similar result. What will happen? Water molecule will attack on the osmium, which will lead to the breaking of this osmium oxygen bond, just like this case. So just like the earlier case, the second oxygen osmium bond breaks, leading to the complete removal of this osmium fragment, and you get an osmium species where you will have two osmium hydroxy bonds and two osmium oxygen double bonds. I hope you can imagine, due to attack of water on this osmium twice, which will lead to the breaking of osmate ester, you will get osmium, two osmium oxygen double bonds, and two hydroxyl groups will be attached here coming from the water. And then when this fragment is completely removed from this system, you get O minus here, and those will be protonated to OH, isn't it? So you get this dihydroxylated product and also this osmium species. So what happens at the beginning of the question, I said osmium tetroxide is highly expensive reagent. Okay, so in the course of the reaction, this osmium species which is formed, the chemists, organic chemists, what they do, they reoxidize this species into osmium tetroxide so that they can recycle the osmium tetroxide reagent used here. Okay, so they used NMO, N-morpholine oxide reagent is used to reoxidize the osmium species formed at the end of the reaction into the initial osmium tetroxide species. Okay, so many times this question is asked that what role of NMO is found in case of osmium tetroxide. Sometimes uh, this question can be asked in exams or maybe interviews. So you have to remember this question, okay? Since osmium tetroxide is highly expensive, the osmium species, dihydroxylated species formed will be reoxidized using NMO. Okay, so moving to the next questions. The next question you have this ozonolysis. Okay, ozone, what is ozone? We have oxygen molecule in which you combine two oxygen atoms via a double bond. You have a species where you combine three oxygen atoms and you get a compound named ozone. Okay, ozone is not very stable, and you can treat alkene with ozone in presence of dimethyl sulfide or hydrogen peroxide, etc. reagents to observe cleavage of this carbon-carbon double bond. Okay, usually carbon-carbon double bonds are very strong and not easy to break, but you can use ozonolysis as a tool to break carbon-carbon double bonds. But what do you get? Do you get alkene or aldehyde or ketone? Let us look at the mechanism of the reaction, how this reaction proceeds. Let us take an example of this alkene, which is tetrasubstituted. Okay, just ignore the substituents. You just observe how the carbon-carbon double bond is reacting with ozone and what kind of intermediates are formed in the course of the reaction and what are the final products that you get. So let us start the mechanism. This alkene, which is tetrasubstituted, will react with ozone. This is the ozone molecule, okay? It is kind of similar to azide, okay? If you combine the three nitrogen atoms, you get azide, which is a combination of So in azide also you observe positive and negative charge present, which will be in conjugation with this double bond constantly. So in ozone also similarly you get such a structure. So now this ozone will undergo 3 plus 2 cycloaddition reaction with the carbon-carbon double bond. How will it undergo cycloaddition? See, this first you can consider this O minus can attack at the double bond. The double bond will in turn attack at this oxygen and this charged oxygen will be gotten neutralized now. You have to just focus on the electron push and pull throughout the concerted mechanism. Okay, all this are happening in a single step. Oxygen negative charge attack to this alkene, and this alkene attacking back at this oxygen, leading to the formation of neutral oxygen at this position. Everything is getting formed in the single step. So from 3 plus to cycloaddition reaction, you get a transition state in this fashion, and out of this transition state you get a pentacyclic framework, and 5-membered framework, which is called mologenite. Due to this 5-membered being in this 5-membered ring, where these oxygen atoms, 3 oxygen atoms are at very close proximity, it is highly unstable and it desperately wants to get broken down and undergo fragmentation. So what happens, this mologenite now, by electron push and pull mechanism, will get broken down into these two species. Okay, you just have to break one oxygen-oxygen bond, because peroxy linkages are highly unstable and weak. So you break this peroxide linkage of one oxygen-oxygen bond, and by pushing the electron pairs from the oxygens to the carbon-carbon bond, you get these two fragments in the reaction. Now what happened? These two fragments are in the same system, so they will also react with each other, but this time they will not react in the same fashion to give the earlier mologenite form, because it is highly unstable. So it will not react to give the mologenite back. Rather, it will now rearrange into a slightly stable Staudinger ozoonite. Okay, you can imagine the attack of this oxide anion to this nucleophilic center, because this carbon of this keto group is very nucleophilic, electron deficient. So this oxide extra electron pair will be donated here. In turn, whatever negative charge will come here, that will attack back at this nucleophilic center. So they will react with each other, leading to the formation of more stable Staudinger ozonide. And it is comparatively stable, more stable than mologenite. Now the Staudinger ozonide will be opened up by dimethyl sulfide aided in the second step. How will it react? See, dimethyl sulfide is electron rich. So the sulfur atom will attack at this oxygen atom, because by attacking at this oxygen atom you are being able to break this unstable peroxy linkage. So sulfur will attack here, the electron will be pushed to this CO bond, and this CO bond will be broken down to give a oxygen negative charge on this one. Okay, so electron pairs will move in such a fashion which will lead to the formation of two more species in the next step. Look closely. Sulfur is donating its electron pair, so it will be positively charged. It is donating its electron to oxygen, but the adjacent bond is breaking, so the oxygen will remain neutral. But at the end of this arrow pushing, this oxygen is getting electron pairs, so it will be a negatively charged oxygen. So the first species you get out of this will be this one, where this dimethyl sulfoxide is associated with this one. After this, you also have this second fragment formed out of this Staudinger ozonide. Now, this charged species, which is like a zwitterionic species, will undergo electron pulling and pushing to eliminate this dimethyl sulfoxide molecule back, and you end up getting the second molecule of carbonyl group. Okay. Thus, you first started with a carbon-carbon double bond, you treated it with ozone, and in the next step, dimethyl sulfide, and you eliminate this dimethyl sulfoxide to get this pair of carbonyl compounds. So now let us move to the original example. What will happen if it follows the similar mechanism? You get breakage of this carbon-carbon double bond, and in turn you will get carbonyl groups at these two carbon positions. Okay. So since this position is broken, this double bond is broken, now you end up getting a planar structure. You get a cyclopentane in which two positions will be substituted. So in this case, you will see a product where both the substituents are going below the face. Why is it so? The reason will be, since you have this bridge in this compound, due to the presence of the bridge and this bridge as well, you get a selectivity of formation of the ozonide. But you must look at the stereo centers which are forming after the reaction is complete. Like, see, here and here you are getting carbonyl compounds, okay? But in the original ring, whatever you had, both these substituents in the cyclopentane ring are on the same side, okay? So after breaking the carbon-carbon double bond, you have to place both the substituents containing containing carbonyl groups. You have to place them in the same side, okay? Because just flatten the cyclopentane ring and imagine where you have to place the two substituents, okay? They are on the same side, they are kind of below the face, so you have to place the substituents in the product also below the face. Thus you get this disubstituted cyclopentane ring as the final product. Then moving to the last question of this session, you have to treat this tri-substituted alkene in the question with hot and concentrated potassium permanganate solution. Okay, the medium is here a hot and concentrated solution of potassium permanganate, and you have to treat it with the tri-substituted alkene given. What will happen? If you study the reactions of alkenes, you will see that potassium permanganate reacts with an alkene in different ways depending on the medium present, okay? Whether the medium is acidic or the medium is basic, etc., etc. So when you have a hot concentrated solution of KMnO4, what happens? First, the manganate ion will get added to the double bond, just like we saw in osmium tetroxide, okay? In a similar way, this manganate ion will get added to this carbon-carbon double bond. And since both the oxygen atoms of manganate are adding from the same side, you get this scene addition. Okay, by scene addition you see a similar manganate intermediate, just like we got in case of osmium tetroxide, we get osmate ester. Okay, here also you get this manganate ester, and you get this 5-membered intermediate when the manganate gets involved with the alkene. So in the course of the reaction, oxidative cleavage happens. It is breaking of the cyclic intermediate happens, and electron pairs get moved in such a way that this carbon-carbon bond gets broken. Let us see how. See, imagine this, between these two, electron pair from oxygen is moving towards manganese because of the presence of these two oxygen here. So in turn, the next bond attached to manganese will get, the electron pair will get donated to this carbon oxygen bond, and opening the ring completely with removal of manganate ion again, you have to open up this carbon-carbon bond. So thus you get a double bond here, a double bond here, and this bond is broken. Okay, manganese dioxide is completely removed from the system. Two oxygen atoms of the permanganate gets associated with the double bond, leading to the formation of this dicarbonyl compound. So thus you have dicarbonyl compound in hand. So let us come to this dicarbonyl state in case of our example. Okay, so what will happen, since you are getting a oxidative cleavage of the double bond, kind of similar to what we observed in the ozonolysis as well, you have to break this carbon-carbon double bond and add carbonyl groups at these positions. And how it is forming is clear from this opening of the cyclic intermediate. So you get a carbonyl functional here, a carbonyl functional here. That means you get a ketone plus an aldehyde. Okay, till this one, I hope it is clear. You have now a ketone and a aldehyde. But what happens in case of hot and concentrated KMnO4, more molecules of potassium permanganate will get associated in the reaction, and it will further oxidize the aldehyde formed into its acidic form. Okay, although it cannot convert the ketone formed into the acid into an acid, the aldehyde formed in the first step will be further oxidized into the corresponding acid. So how it is happening, let us see. Let us start the further mechanism, like how the aldehyde was converted into its corresponding acid from here. Okay, just focus on this aldehyde. In the system, hydroxyl anion present will attack the nucleophilic carbon of the aldehyde. Okay, this carbon atom is highly electron deficient, so hydroxide present in the system, you can imagine from water molecule as well, will attack at this nucleophilic carbon. The electron will get pushed to this oxygen to give you an oxygen anion here. and you get this anion in return. Now this anion will react with the second molecule of potassium permanganate. Okay, this oxygen will attack at the metal center of permanganate, leading to the formation of oxygen anion at this position. So you get oxygen manganese bond formed. Now one manganese oxygen double bond will extract a proton from this carbon, which is containing the oxygen atom coordinated with the manganese. One MnO double bond will extract this proton to break this carbon hydrogen bond now, and the electrons of the bond will be shifted to this carbon oxygen bond, and the manganate will be knocked out. Okay, so you end up getting the corresponding acid of the aldehyde formed, okay, in this way, where a hydroxyl ion from the system also comes into picture, and then you react the anion with the second molecule of permanganate, leading to the formation of corresponding acid. So this species, whatever formed, underwent intramolecular proton transfer, and the arrow pushing will show the byproduct, which will be a manganese atom, which will be connected to 4 oxygen moieties in different forms. Okay, one will be hydroxyl, 2 will be MnO double bonds, and 1 will be oxygen anion. Okay, this can also pick up proton from the system, but since there is no acidic presence is shown here, maybe it will be in a charged species, but mostly from moisture it will extract a proton to get neutralized and finally contain 2 hydroxyl groups here. Okay, that will be the byproduct. So as the final product from the aldehyde, you get this corresponding acid. Okay, so thus we started from this alkene and treated it with potassium permanganate, hot and concentrated solution. So you get oxidative cleavage of this carbon-carbon double bond and get this ketone and this acid. Okay, so with this we have come to the last question of the session. Let us go through the questions again, whatever we have discussed today. First, we quickly went through the various kinds of reactions that an alkene undergo. A number of reactions they undergo because an alkene mostly undergo electrophilic addition reactions because of the presence of their pi bond. Okay, the pi bond is highly reactive, and in these reactions you can see breaking of the pi bond and the addition of 2 groups across the pi bonds. Okay, so this kind of reactions an alkene can undergo. So in today's session, what we did was, via examples, we tried to understand the mechanisms followed in these reactions. Okay, at first we saw how an epoxide react with acidic medium. Okay, how an epoxide ring is opened up when it is treated with acidic medium, and we saw that as a final product you get a trans 1,2 diol. Okay, so this was a product. Why it was trans, that also we discussed. It is coming, the justification was coming from the molecular orbitals involved in the donation. So the attack was taking place from the opposite phase to give a trans 1,2 diol. In question 2, we saw how this alkene, substituted alkene, was reacting with hydrochloric acid, and we went through the mechanism to see that always the reaction pathway prefers formation of a stable carbocation. Okay, and in the final step, the counter anion present or whatever nucleophilic species present in the system will attack the carbocation to give this neutral saturated product. Then we also discussed how this acyclic alkene moiety reacted with hydrochloric acid, and we saw that here as well the more stable carbocation, secondary one, was formed. This one was kind of an exceptional example where although we got a secondary carbocation uh, as one of the possibilities coming from this double bond, like over the primary one, we first got the secondary one, but since a subsequent shift from the adjacent carbon could give us more stable carbocation, so we went ahead with methyl shift in the reaction and we obtained the more stable tertiary carbocation. Okay, so this was a very important and exceptional example in this case. Then we also observed how this indene moiety reacted with hydrobromic acid, and we saw that this product containing bromine atom at the junction was formed. Then we again went ahead with an exceptional case where hydride shift was taking place in the mechanism and we got a tertiary carbocation which was more stable, and we obtained this product as a major one. In the next question, we found how alkene reacts with acidic medium and water adds to the carbocation formed as a nucleophile. We also treated 3-methyl-1-pentene with acidic medium, and hydride shift was observed here to get a tertiary carbocation, and this substituted alcohol we observed. Then we also went through the reaction of alkene with mercury acetate in water to get a Markovnikov regioselectivity in the product. And we got this mercury acetate in first step, which underwent reduction with NaBH4, and we got an alcohol as the final product. In the next step, the similar reaction happened in this alkene as well, and we got this alcohol as the final product. Then we learned how hydrogenation in presence of metal catalyst take place. We talked about the concept of adsorption and how this hydrogen molecule and alkene gets adsorbed on the platinum surface and get added to the alkene to finally give a saturated compound. Then we learned the mechanism of bromination and dichlorination of alkenes. We talked about bromonium ion formation and attack of bromide from the opposite phase. Similarly, in chlorination also, the similar case happened and we observed anti-addition of chlorine atoms. Then we also talked about reaction of alkene with peracid, how electrophilicity and nucleophilicity comes into picture, and we got an epoxide first which was opened up by water molecule due to the presence of water and acid in the system, and we finally got this dihydroxylated product. Then in presence of osmium tetroxide, how alkenes reacted, we saw that osmate ester formed in the course of reaction, and water molecule opened the osmate ester to give a dihydroxylated product, which is a syn dihydroxylation. And we also talked about how reoxidation of the osmium species took place in place of NMO. And then we went to ozonolysis in presence of dimethyl sulfide of this alkene, and we observed that the mechanism went through the formation of monogenide and Staudinger ozonide, and how the Staudinger ozonide was opened by dimethyl sulfide, and we finally got this cleavage of carbon-carbon double bond to get this dicarbonyl compound. Then we lastly talked about treatment of alkene with potassium permanganate hot solution, and we saw that in presence of hot solution of concentrated potassium permanganate, you first get a permanganate ester similar to osmate ester, and you observe oxidative cleavage of the double bond to get dicarbonyl compound. But since potassium permanganate is very strong oxidizing agent, it further oxidizes the aldehyde species whatever formed to its corresponding acid. Thus, we got a ketone and an acid as the final product. So, like this, we have discussed a few mechanistic approaches on the topic reactivity of alkenes today. So, thank you everyone for joining. Thank you for patiently listening. And if you have any doubts or queries, you can feel free to ask. So, thank you everyone.